Hello, and welcome to the 6-5 Summit. I'm Shelley Kramer, one of the founding partners of Futurum Research. And on behalf of my team at Futurum and the team at Moor Insights and Strategy, welcome. We're so glad to have you. In this spotlight session, Patrick Moor of Moor Insights and Strategy talks with Darío Gill, the Senior Vice President and Director of IBM Research, about the technologies and innovations that IBM is creating to deliver the critical outcomes that customers need in today's digitally transforming world. This is a conversation I have been waiting for, so let's get to it. I think it's going to be terrific.
Darío, welcome to the 6-5 Summit 2021, and I just want to thank you for speaking here on day 4.
Thank you so much, Patrick, for inviting me.
Yeah, we have some really great IBM speakers, and you are one of them, and it's great. You know, we had head of strategy, and now we have head of research. But before I dive in, maybe I'll let you introduce yourself and what you do at IBM.
Yeah, as you said, I'm responsible for research for the entire company globally, and I would say overall for the technology roadmap and the technical community of all of IBM.
Oh, I think that's great, and that spans so many different areas: hardware, software, cloud. I mean, I'm really impressed at what you guys do here. Can you talk about what IBM Research does and why it exists? You know, one thing I love to point out to everybody is, you know, we always say R&D, right? And they're so different. I don't know why we call it R&D, because research is farther out. It's risky. It's not definitively tied to an exact product. Sometimes it works, sometimes it doesn't. And development leverages all the research and hard work that is done out there. But I guess we put it on P&Ls as R&D, so we call it R&D.
I mean, you're so right about that, and the horizons are different, and the risk is different. And you know, the first observation I would make is that the research division of IBM has existed for 76 years. So one of the reflections, the first reflection I would put forth is that given that we've been in the information technology business as a company for 110 years, and is the only company that has been able to do information technology for over a century, it begs the question of why others haven't, right? Or what is the difficulty? And that is that integrated over time, you know, in an industry that changes so dramatically, is the normal course of events is to disappear. And what I would say is like the reason why IBM has been able to survive and to be able to do these advances throughout all this period is really because we've had a research division that is able to look across different horizons. So I agree that one characteristic of it is you can take on a lens that is more risky, right? Some things don't work out. That's the nature of science and the nature of research activities. And you know, and another one has to do with the composition of the teams that conducted work, right? So you know, it's composed of lots of scientists that you know are really focused on applying the scientific method in our context for the world of new ways to process, store, and use information in creative new ways. So it is, in the end, I mean, there's a linkage. Let's not overpush it, right? Like you gotta then derive the value from research to development and make products, but they are distinct fields.
Yeah, and I think it would be valuable to maybe talk about how ultimately the research that you do does end up positively impacting your customers, or what IBM lovingly refers to as clients.
Yeah, no, that's right. I mean, and the ultimate value is to make sure that that impacts. So let me give some examples. So let's say, you know, since, you know, I know we're going to be talking about semiconductors and the world of hardware, if we look at the world of systems and if you look at our mainframe franchise, so you go and you say, wow, how can a product, right, you know, a franchise last that long, that many decades of generation after generation of delivering value? And underneath it is because we reinvent it every generation. And there is a heavy, heavy element of research that goes into it. from the design and novel architectures for the microprocessors to the core semiconductor technology that we're able to use. So if you look at many of the seminal innovations in the semiconductor industry that have taken place over the years, from copper interconnects to high-k metal gate, and many technologies, they were created by research in IBM, as an example, in the context of impacting that product. If you look at the world of software, we see similar things happening, right, with our Watson portfolio and AI. But I'll give you another extreme, which is a net new market, a whole new industry like quantum computing that originated, here in research. And after many decades of work, we're now seeing its commercial realization.
Yeah, I have to point out that Intel CEO Pat Gelsinger, he led the keynote a couple days ago. I know he's a customer, and that was super exciting to see them sign up with IBM Research. And also on the slides is Samsung. And so you have number 1 and 2 largest semiconductor manufacturers publicly working with you. And I think we both know that what's not public is a lot more people than the number 1 and number 2 semiconductor folks.
Yeah, what there is a testament is on the respect and the value that a very broad ecosystem of industry leaders pay to the research prowess of IBM. Like, across the research division, we employ 3,000 scientists, right?
Yeah.
Well over 2,000 PhDs. And if you look at our Albany ecosystem that we have created now over 20 years to create the world's most advanced semiconductor collaborative environment for R&D, in this case, it's attracted leading equipment makers, the leading EDA, companies. But you're talking about now the semiconductor manufacturers, right? Companies like Samsung and now Intel. And what's beautiful about this is that we gotta leverage the strengths and the complementary strengths of all the different players, all the different companies. But it's a reflection of that respect and that value for investing fundamentally on research that is the reason why we keep collaborating and expanding the ecosystem. And indeed, the Intel announcement, if you you ask me, and I'm sure like you a few years ago, and say like, wow, would you imagine Intel and IBM working together in semiconductor? Would say, oh, that's not possible. But it's a testament of, I think, Arvind's leadership and the approach to ecosystems, of Pat's, the transformation agent that is coming Intel. And look, what would seem impossible now is a reality, right?
Yeah, I had to go back and search for IBM and Intel alliances, and I think I had to go back to before when I started working in the 80s. It had been a while, so it was good to see. And you had a really big announcement with 2 nanometer that I know sent shockwaves for the industry. I know that it's funny. You always read, oh, we're not going to get to this lithography, or we're hitting a brick wall. And the industry always finds a way, and IBM found a way to, you actually had a working product at 2 nanometer. Can you talk about that a little bit?
Yeah, I mean, we are incredibly proud of the work of the team. It's the fruit of like 4 years of work. So this is based on transistor technology called nanosheets. It's a form of gate-all-around transistor. We had announced actually about 4 years ago the introduction of the nanosheet technology for the 5 nanometer node as well. And now we've been able to demonstrate after 4 years of work that the whole technology, could be designed for the 2 nanometer node. And what is going to mean is that we are going to be able to design chips that are going to either improve the performance by about 45% compared to 7 nanometer technology, or reduce the power consumption at the same performance by 75%. So it's a real breakthrough. We're incredibly exciting, and we really believe that it is going to be the core technology that is going to be used by the whole industry.
Yeah, and I may have used the wrong word, device, 2 nanometer device, which that technology will make its way into both Power and Z. And the rest of the industry, but we can't talk about that, of course. So other announcements you made, I think, were pretty exciting, and sometimes people gloss over these, but you actually have developed a system that uses artificial intelligence to inspect code and to be able to help developers move to the cloud. So let's say you had an application that was written 20 years ago. You put it into Codenet, and essentially it tells you what's used and what's not. And I'm kind of stealing your thunder here, but it's so exciting, I can't help myself. So why don't you talk about it?
It's I mean, it's actually had a tremendous impact, and there's just so much excitement externally on the community and on the open source. So here's an analogy I would provide. We're all familiar with the impact that ImageNet had, I would say in the late 2000s, early 2010s in the world of AI. So what was it? It was the curation of a massive data set of images that had labels, and combined with large-scale neural networks, deep learning, and compute power, it transformed how computer vision was being done, and image processing, and we've witnessed the last 8 years of the deep learning explosion. So this thing, by analogy, we actually purposely named the data set CodeNet, right, like ImageNet. And what we've done is a massive data curation engineering effort where we have taken tens of millions of lines of code of all sorts of languages. I mean, we're not talking only about contemporary Python and C++ and Java, but we're talking about COBOL, right? And things that are there that we've learned that people use quite a bit still in in payroll benefits in New Jersey remember when in the middle of the pandemic, when they were expanding unemployment benefits, and people were saying there's a shortage of COBOL programmers, right? So it actually, if you look at the economics of this, it takes about something like 50 cents a line of code when you have to do this manually to convert it. So what have we done? We've curated a massive amount of sample programs that are written in different languages. And just like that curation in the past with languages enabled simultaneous translation, right, using statistical machine learning, the idea is to use AI and train large neural networks to be able to do this code translation. And it begins by curating these data sets and using compute power. So I think that if you just look at the productivity potential of software engineering assisted by AI, software is like the lingua franca of business. So enhancing the productivity is massive.
Yeah, it is, and getting people to a cloud model is important. And it's so funny. I remember Y2K. We had a shortage of COBOL programmers. I'm thinking, okay, we're in 2021. There's probably an extra shortage out there. Actually, IBM and the Z team has done a great job on keeping COBOL moving forward. Let's hit one more. It's funny. Real time or near time technology here called Kiskit. So we sometimes think as quantum computing is 10 or 15 years from now, and we talk about, hey, isn't this hardware beautiful? And by the way, you have some of the most beautiful hardware that exists out there, but there's real software and runtimes that go along with that. Can you talk a little bit about the Kiskit runtime?
Yes. So Kiskit stands for Quantum Information Science, software kit, Kiskit. And it's like the world's most popular open source environment to do development in quantum computers. And what we announced is the creation of a runtime where now you have the combination of classical and quantum resources, tightly interlinked, so that when the user creates a program, all of that happens behind the scenes. To be able to execute the program very, very efficiently. And what we demonstrated in doing Think, it's 120x speed up compared to what you could do when you're just using your laptop, right, as the environment to be able to orchestrate the productivity of the quantum program. And what we have to remember is behind the scenes, you're going to have these quantum circuits that are going to be running in the quantum computer. And you're going to need to execute hundreds of millions or a billion of these quantum circuits to be able to create value from an application. So the productivity of the software environment, it's a massively important effort of it. And we're just, incredibly excited about the fast growing ecosystem and really the advancement of the runtime, as you mentioned, to be able to create a whole new generation of applications. And I'll just give you one fact. Today, at any given day, we run now over 2 billion quantum circuits a day. So it's a fantastic, we've seen a sort of this exponential growth of the community of learning how to program and creating this new generation of applications. So we need to envision these frictionless software development environments.
Yeah, so literally real time, we're talking about shrinking lithography down to 2 nanometer with nanosheets. We have machine learning and AI writing its own programs. And we have real quantum runtimes out there to make real applications in the future and actually develop algorithms for today. So, but this is where you get paid the big bucks here, Darío, which is about the future. I want to talk about the future and get out your crystal ball here. Actually, I'm sure you have a plan. It's more than a crystal ball, but let's say beyond 2 years. I know you go out a lot farther, but every year you go out, it gets a little foggier. What are we looking at 2 years from now?
So these three trends that we have talked about, which I summarize about, the future of computing is bits plus neurons plus qubits, right? So high precision transactional processing, the world of neural networks and artificial intelligence, and the world of qubits. I think the part that is not sufficiently understood, right, by the industry is that each one of those we understand is a massive market and a massive roadmap, and we work and invest very aggressively on advancing each. But I think the part that people don't sufficiently understand is what's going to happen with their convergence. What happens when you actually architect systems in a hybrid cloud environment to be able to bring together the best of those three worlds? And I just want to tee off an opportunity that we're very, very focused on, which is just to elevate it. What do I really believe? What I believe is that science and the scientific method needs to be elevated and diffused more broadly across society to be able to solve the most existential problems that we face. I mean, and the public is experiencing the power of science in a way that I don't think they have experienced it in their lifetime, which is with the development of the vaccine in record time. So imagine a world where we can compress that time to discovery. So what we're really focused is about creating this next generation of architectures and systems to be able to bring the best of bits, neurons, and qubits to accelerate scientific discovery. And if we did it, it would be like the mRNA platform for vaccines, but for the world of scientific advancement at large. So that's the mission that we have, the component technologies, their convergence, and a purpose, which is the scientific method accelerated.
And let me make sure I get this right for the audience. Bits, neurons, and qubits?
That's right. Bits plus neurons plus qubits is the future of computing.
You need to get that on a license plate or something, BNC, before somebody jumps on that. No, that is super exciting. And you can't get everything from the past, but it can give you an indication of how some things can come together, and then using the art of the possible to pull that together. And this combination of creativity, right brain and left brain coming together to create the future, I think is fascinating, and it makes pedestrian things like quantum, right?
Hardly pedestrian.
Look easy. I know I'm joking, of course, but the way that I've seen GPUs leverage traditional computing in a similar way, that this is my expectation, I think it's yours, of how we get our first practical toe in the water on quantum beyond very important algorithms that we're doing. It'll be a combination of a traditional program accelerated by quantum. Okay, and whether you want to call those the bits that are being used, or you're referring to things like 2 nanometer, but it's this combination of these three things that create some pretty exciting things.
That you're exactly right, and I think we've in the industry talked so much about what happens at the limits of Moore's law and what's after, and what I think is exciting is like we actually have an answer to what's happening. Is that we keep pushing the limits of it, right? That's a 2 nanometer example and beyond. But beyond that is really this. It's really architectural diversification and their combination. And it's a combination of these three architectures that are going to represent the next, many, many decades of advancements. And we're seeing that innovation is happening through the entire stack on each one of those elements. I mean, the nanosheet technology is a good example of that. But if you look at AI, beyond reduced precision architectures, we're investing very aggressively in Albany as well on analog architectures for AI. And then if you look at quantum, it's a whole other, set of devices based on the transmon cubic, with superconducting technology and so on. So what you're seeing is across the stack, these beautiful new integrations are possible. And I guess the point I'm making is that in addition to that, we're going to have the implications of the architectures of combining them. How much classical versus how much quantum? Right. How much AI versus how much of like the high precision? That in its own form is going to be a form of engineering differentiation.
I want to dial us back a little bit. Let's pretend we're 2 to 5 years out. How do bits, neurons, and qubits make an impact on the cloud? And listen, there's new things in the cloud all the time. Just when we're all settled on containers, we see serverless, right? And new things will come up. But how do bits, neurons, and qubits, how might that affect our cloud environments moving forward?
Yeah, it's a great question. So what we need to do with hybrid cloud platform is two fundamental trends that are important to wrangle the complexity of this heterogeneity that is underneath and mask it for the user, right? We don't want the user to have to think about like quantum physics, right? We want to enhance their productivity as developers and as users of the overall system. So what do we need to do that? My view, like on this, and the philosophy that we take in IBM is that you need a thin layer of interoperability, and it's based on open technologies and the right abstractions. So open. There's an answer to what the operating system is for this, which is Linux. And then on top of that, right, in terms of like wrangling that complexity, on top of that, you need the right abstraction. Containerization is a wonderful example of the encapsulation of software and abstraction, right? And we've seen in this evolutionary battle of this abstraction that Kubernetes has emerged as the dominant form of this kind of orchestration. But you use the right trend of what is happening, which is the world of serverless, which is you need to even raise even further that level of abstraction such that the vision in the end needs to be that massive amount of compute power, heterogeneous, that is across multiple clouds, private and public, multiple public ones, for a user should feel, this is the ultimate vision, as if it was a single computer. And we're accustomed to sitting in front of our laptops and doing file transfers, doing things like that, programming and so on. Imagine that, but behind the scenes is this hybrid cloud infrastructure. That is where we need to be able to get to through open technologies and abstractions.
So Darío, every time I talk with you, I pull something back. And I love this whole trifecta of bits, neurons, and qubits. You may have said it before, but it didn't internalize with me, and I'm sure it's going to be new to our audience. But doing this in an open and at the right level of abstraction to deliver this one looking computer that can be many computers, but it looks like one. Wow. I'm gonna have to think about that for a while. I think our audience is going to have to think about that as well. So I just want to thank you for coming on. I mean, I could do this for you for the next hour, but people might not want it to be that long. But if they do, they can come find all of your videos. You did a pretty cool one for Think that I thought was very cool, that gives the full double click on what you're doing. But listen, for the sake of the industry and IBM clients, I thank you for what you and your team are doing. There's not a whole lot of research being done anymore. I mean, I could count on both hands when I first started my career over 30 years ago on who was doing research. And I can name which one of them just got out of it for various reasons. But thankfully, IBM has hung in there and delivered results because, listen, if there aren't results, then there's no funding, and that's life. But I'm really glad to see that you have, because you just keep cranking them out there. But anyways, Dario, thank you so much for coming on the show.
Thank you for inviting me to this event. And Patrick, the feeling is mutual. I always learn a great deal from you as well, right, in the conversation. So, and I look forward to future ones. Thank you.
I appreciate that. So this is Patrick Moorhead with More Insights and Strategy. Hope you're enjoying your day 4 at the 6.5 Summit. Take care.